So if we open the point in Polygon notebook here, we will later be using the addresses that we geocoded and doing some spatial analysis on that. But first, a little bit of conceptual thinking about what point in Polygon and intersect analysis is. So if you have experience in GIS from before, you might know these terms already. So point in Polygon is basically a analysis of finding out if a point is, as a sound, within a polygon, or the other way around, if a polygon contains one specific point. So in Python, there are two shapely functions that we can use to do point in Polygon analysis, and those are called within and contains. So within is handy to use if we want to check if we have a point and we want to check if that point is inside of another polygon. And then contains is the other way around. If we have a polygon and want to see, does this polygon contain a specific point, for example. So yes. So yeah, even though the analysis is called point in Polygon, we can also check other types of shapely objects like line strings or polygon, polygon in Polygon, line string in Polygon, but we all call it point in Polygon operations. So let's start here with the already written down code cells. We are importing from Shapely. We will be using both points and polygons. So let's import that. And then we will create two different points that we will use. So we'll just run these cells and also create this polygon from this list of coordinates tuples. And then we can print them out to see how they are going. Yes, so we can see we have 2 points as shapely objects and 1 polygon also as a shapely object. So then to start with the point in Polygon analysis, we can check whether whether the points are within the polygon that we created. So to do that, we can simply take our first point, P1, and then use the function within and see if it's within the polygon. So if we run that, we get a true. So yes, it returns that the polygon is, or that the point is within the polygon, and we can do the same thing for our second point, P2 within poly, and see that it returns false. So yes, it seems that the first polygon, the first point, sorry, is within the polygon, but the other point is not. So we can see, just to investigate a bit further, we can, if we print out our first point and the centroid of our polygon, we can see they are quite close. So naturally, the first point would be within the polygon. And then we can also do it the other way around, as mentioned. So we can start with the polygon and see if the polygon contains, using the contains function. And if it contains the first point, that should be true, and it is. And then we can check the same thing for point 2, which it doesn't. So as you see, they work. They provide the same result. They do more or less the same thing, just in different kind of orders. But there might be sometimes when you want to do a within analysis, and sometimes you want to do a contain analysis. That depends on what kind of data you have. So if you have a lot of points and just one polygon, and you want to try to find out which of the points that are inside the polygon, then it might be easier to just iterate over each of the points, see are they within this polygon. But then vice versa, if you have a lot of polygons and just one point, and you want to see which polygons contains this point, then it would be easier to iterate over the polygons and do a contains analysis. Okay. So on to Intersect, which is another geospatial analysis operation that we can do. Here we want to see whether a geometry either intersects with another geometry or if it touches it, but not necessarily that they contain. So usually this is more common with line strings or lines. So we will be doing here to try to see how it works. So first of all, we can run this code cell that imports line strings and multi-line strings, which we will use, and then create two different lines, line A and line B, in just this arbitrary coordinate reference system. So one way to see if they intersect with each other, we can start with line A, and see if it intersects line B, and it returns true. And we can also see if they touch each other. So line A, if it touches line B, and that is also returns true. So let's just try to quickly plot the two lines to see if it makes sense that they both touch and intersect each other. So one quick way to do that you might have run into in the last week, in the last week's exercise, is we can create a multi-line. Let's call it multi-line string. And then to create the multi-line string, we pass it a list of different lines. So a list of line A and line B. And then if we just type multi-line, it will plot it for us. So here you can see that they both touch and intersect. They share one point in the corner here where they overlap. So indeed, they both touch and intersect. They both share, as we saw up here, they both share a boundary and interior of each other. So what we could also do is to check that if lines don't fully overlap, or if they fully overlap, that then they don't just touch. So we can see if line A, conceptually, we can see that if line A touches itself, it shouldn't do that because it can't. It will then, that will return false. But we can also check if it intersects with itself. If line A intersects line A, and that it does, that returns true. So if we just take one step back and look at what the functions actually check. So intersects checks if two objects intersect if the boundary or interior of one of the objects intersect in any way with the boundary or interior of the other object. And then touches is if the two objects touch, if objects have at least one point in common and their interiors do not intersect with any other parts of the other object. So in that sense, line A does intersect with interior, any different, the whole line itself. So in that sense, it doesn't touch, but it intersects. Yeah. Okay. Then we can try to see how we can do point in polygon analysis in Geopandas. So in this instance, we will be reading in the data that we created in the previous notebook. And that is also should be in the data folder already if you weren't able to do it with the geocoder. But we will start by importing Geopandas as GPD and then reading in our data file. And then we can double check how that looks. So here you will recognize the same data that we got in the last notebook. We have the addresses and the geometry and the IDs of all our addresses. And then we will try to see whether which of these addresses that are located in one specific district of Helsinki. So for that, we will need a file of the different districts in Helsinki, Polygon file for that. And that we have a KML file in the data folder for that. So here we so KML files, as we touched upon last week, is not necessarily readily available to use in Geopandas. So if we see the list of supported drivers, we won't find KML. So we just need to activate the support for that. KML files is a bit old file format and it's a bit technically difficult to work with sometimes, but it works. And it works for our purposes. So if we run this cell to activate the KML driver, we can double check the list of drivers and we will see KML at the end here. So then we should be ready to read in our KML file of the different polygons of Helsinki. To do that, we have the file path here to the KML file, and we will use Geopandas to read it in. So let's call this layer polys for polygons and use GPD read file. We will do the file path. And then since it's a KML file, we will specify that the driver to use is KML. So we read in that data, and then we can check the length of the, let's do a print len of polys, if I can write that correctly, and then also just take out or look at the head of it to see what it looks like. So here you see that we have 23 polygons, 23 rows in our data, and we can see that we have the different the names of the polygons and also some polygon objects to work with. So that is good. We can just quickly plot the polygons also to inspect them and see that they somehow resemble Helsinki. It contains also the water areas, so that's why some of the districts looks a bit strange, but at least this looks more or less correct. So we will be trying to figure out which of the addresses of the stations that are in the addresses list, which of those are located in one specific area. So we will be using the Eteläinen area of Helsinki for a point in polygon analysis. So let's create a new variable called southern, and then select only that one district. So from our polys data frame, we will locate one row, and that row is where polys, where the name of that is Eteläinen. So polys, and then it will look for in the name column and give us the matches that of that. I'll just copy that name. So Eteläinen, it will then, yeah. So what we do here is within the polys geodata frame, we locate this condition, which is where the name of the polys is Eteläinen. So if we run that cell, we can even take a look at southern and see, okay, here it returned only one row of data. There was only one match for Eteläinen, so that is good. We have located that one, but we can also see that the index, which we talked about also last week, that the index doesn't necessarily make sense when we only have one, when we have done this kind of location analysis in our data frame. So let's reset the index for this. So we can do that by doing southern and then reset index, and then pass the parameters drop. This will then drop the index that is already there. If we didn't want to drop it, it would create that as a column of its own, but we don't need that, so we will drop it and then in place true to replace the index in the new place. So if we then take a look at southern again, down head, then we see, okay, that we have one polygon in our data frame for Eteläinen. Good. So what we can do now is to try to first create a map to see all the different components that we have created so far, to see where we are at. So we will create a plot. Let's create a figure with one subplot, plt.subplots. We will just do this as a simple plot. So first we can try to plot our polygons. Let's start with our original polys. Plot that to the axis, and let's give this a color. We will go with gray. So if we just ran this at this stage, we see that we have plotted we have all our districts polygons. So if we, on top of this, plot the southern polygon, we can do that by southern dot plot also to the same axis, and then give it a different color to make it clear. We can do that in red. So if we plot that, we see we have only had this one district in the southern geodata frame that is located here. So that looks good. And then we can try to plot our points data on top of that to see where all the different points are. So the points are in data. So data dot plot to the same subplot axis, give them a color to distinguish them. We can do that in blue. And then as these are points, we can give them a marker size as well. So if we then plot that, we can see all the different points are plotted on top of the districts, and we can see a lot of the points are located outside, but some are also located inside of our southern polygon. So the next step to do then is to try to figure out which of the points is it that are located in our southern polygon. And for that, we can do a point in polygon analysis or operation. To do that, we can first check if we have something called speedups in Shapely enabled. It's something that runs in the background and then makes the spatial queries that we're doing faster. So it should be enabled in CSC from when we boot it up. But if you are working on your own computer, you might have to make sure that you enable speedups from Shapely just to make things go a bit smoother. So just run that cell, and then we can start with our point in polygon analysis. So what we want to do is to check which of the points in our data frame that are within the southern polygon. So if we can start to look at that. If we type data and within, which of these address points are within southern, and then we want to make sure that we're looking in the polygon object. So to do that, we can type at and then the first index of our southern geodata frame and the geometry column. So if we run that cell, we have done a within operation that returns a series of all the different points and which of them are true. So true here is, are they within? Yes. And false for those points that are outside of our southern polygon. Okay, I hope that made sense. Let's then store this output in a variable. Let's do point in polygon shorthand pip and pip mask. So yeah, if we type pip mask here, it should return the same series. So a series of Boolean values, true or false, which we can then use to locate these points in our geodata frame that we have. So what we will do here is to use the kind of mask to subset or to select the data from, to select all the points that are true and not just the Boolean values here. So if we, in our data frame, try to locate the pip mask that we just created, it will then find the points that are true. And let's save this in a variable called pip data and check out what that then contains. Then we can see that we not only get the Boolean series here, but we get a data frame of the different points that are true. Okay, did that make, I hope it made sense. We can then try to plot it to see if it, see how that looks. So I will let's just speed things up and copy the plot from above. Scroll down and paste it here. But instead of plotting our all our points from our addresses, let's plot just our PIP, point in polygon analysis data that we did above. And just change the color so that it's a bit different. And if we plot that, then we get a plot with only the points that are within our southern polygon. Okay. So that was the point in polygon analysis. So both, yeah, we can just recap quickly what we did. We read in, if we scroll back up, we read in the data from our geocoded, or we read in our geocoded data, and also the different districts of our data set, and then selected only the one district that we were interested in, and then later on created a mask, did a within query, saw which data points are within our district of interest, and used that mask to select only those points from our original geocoded data set. Okay, super. So we can continue with spatial joining. So that if we open the notebook number 3 today, called Spatial Join, we will be doing, in a way, a bit similar to what we did in the last notebook. We will be joining data from one data frame or geodata frame to another. But sometimes we also want to do that join based on the spatial relationship between the data. And that is where spatial joins come in. So what we're going to do now is to apply some of the techniques that we did in the point in polygon queries, and then perform a spatial join between two different layers to get the attributes of the two different layers that we're joining in together into one final data frame. So we will still be using the same techniques and concepts from before, but in spatial joins, it is already implemented in Geopandas, so so that is readily available, and we can do that with 3 different types of joins that will sound familiar. And so in our spatial join function in Geopandas, there's a parameter that is called OP, or it used to be called that, and it still works, but it's also changing name to predicate. So those will be using, it might be that I am using it interchangeably, but they're doing the same thing. But in the future, we will continue to be using predicate, which is just called from now on in Geopandas. But we will be using the intersects within and contains types of operations and spatial joins. So they work in the same manner that we discussed just before in the last notebook. So the spatial join function takes the predicate parameter, but it also takes a how parameter. And that is, you can pass it either left or right or inner based on what kind of join you want to do on the 2 data frames. we will get back to that and see some examples of how we're using it. But first of all, we will be using two different spatial layers here, and we will be using the addresses from before that we geocoded, and then we will be reading in a population grid from the Helsinki Region Environmental Services. They have a web feature service where we can read in data. So here in this first code cell, I'll just run that, and then we can talk through what it does. It specifies a URL to the web feature service, and then we create a dictionary of different settings or parameters that we need to pass on to the web feature service request. And then we use the requests module to send that request to the web feature service, passing it the URL and our different parameters. So our parameters defines what type of request we're sending, what data we are looking into, and what format that we want to get out of the request. So we run that request and load that outputting JSON file into a geodata frame called POP. So what we're looking at from the web feature service is the population data from 2018. So we can start by taking a look at the our resulting, or the output from our request. So take a look at the head of the POP geodata frame. We can see that we get a bunch of polygons that have an index on a population count, and some density and data for the different age ranges. So as you see, there is a lot of data in the data frame. We won't be needing all of that. We will only be using some of it. And let's also, for ease of use, rename the population column that we are interested in. So let's start by cleaning our data in that way. We will start by typing pop, and so taking our geodata frame, and then we want to rename that, replace it with the renamed columns. We want to rename the columns, and then renaming columns, we pass it a dictionary, and we want to we pass it a dictionary of the old name and then the new name in key value pairs. So let's just I'll copy the column name that we want to rename, and then colon, and then pop 18 for population for 2018. And then we can just check the columns to see that that is done correctly. We can see our new pop 18 column here. So that's good. We renamed the column that we want to use. And then we don't want to use all of the different data, so we can easily subset our data into just the columns that we need. So let's do that by taking pop and then replacing that with selecting only the columns that we want. So we then select a list of the columns. We will be needing the population column and also the geometry column. So this is just an easy way to make working with the data easier, to only select the part of the data that we want. We could always rerun the request and get the original data back if we wanted. But now we are just working, storing less data in our memory, so it makes it quicker to work with. Okay, we subsetted the data. Let's take a look at the contents that we have now. we have the population count number, and then our geometry column as well. So that's good. Now we have cleaned the data that we want to use. And then now we are on to joining the population data together with the addresses data. So let's read in our addresses that we created earlier, and we can take a look at the addresses ahead. That is familiar. We know that data frame already. So what we want to do an important thing to be aware of when joining different data is to make sure that we're joining in the same coordinate reference system. So let's have a look at what the coordinate reference system of our two data sets are. So let's start with the addresses, and we can check that by .crs. See what we get here. We get the VGS 84 coordinate reference system with the EPSG code 4326. So that is good. And then let's also take a look at the population data, what the CRS is there. So we can, when we run that, we don't get anything because the CRS is not defined of the data that we got from our web feature service request. So we could go into the population grid metadata and look up what the CRS is, but we have done that already for you. So we can we can define the CRS from the EPSG code that we know that the population data is in initially. So we will take our pop data frame and or we will take when we define the CRS, we will take the pop CRS and then use the CRS class and we have the EPSG code. So we will go with from EPSG and use the 3879 EPSG code 3879. So if we define that and then again run pop.crs, then we get that it's a projected CRS with the name ETRS 89 or GK25 fin. And we can see that it's it's a Cartesian projection with meters, using meters, so that we can measure distances, for example, from this coordinate reference system. So that is good so far. So, but when we need to join the two different data sets, then we need to make sure that they are in the same projection. If not, then the addresses data set will have very different coordinates than our projected data set, even though they might be in the same place. So we can then check if our addresses CRS is the same as our population CRS, which it is not. So then we need to reproject one of the data sets to match up with the other. And so in one sense, it doesn't matter which way you do it, but it depends on what kind of analysis you want to do in the end. And also here we have one with a Finnish coordinate reference system for our data set that contains a grid of different polygons. And polygons are more complicated objects than points. So our addresses points are easier to reproject than our population polygons. And it's less prone to error if we reproject the points rather than the polygons. So let's then go ahead and run this cell that takes our addresses data frame and .to CRS. We use the reprojected into the CRS of our population layer. So if we run that, that runs smoothly, and we can then print out the different CRS of the two layers. So if we first print out addresses.crs and make sure to type that correctly, and our population CRS, and we can also check if they are exactly the same. So addresses.crs equals population.crs. So we see they have the same EPSG code and they are matching. So that's good. That means we have cleaned our data and made sure that we are able to do a spatial join without making any errors there. So this is a good rule of thumb to always make sure that you check if the layers you are joining, if they have the same CRS. So if you're writing functions or longer scripts or codes, to always have like an either assertion or something that gives you an error or warning if your two data sets doesn't have the same CRS. So you can fix that before doing the spatial joins. Okay, but we have made sure of that now, so we can get on to trying to join our two data sets. So the goal that we have is to get the attributes from our population data into the addresses data with a spatial join. So we will make a new variable called join, and here we'll use the Geopandas sjoin, and then here we first take the addresses, and that's what our starting point, and we want to get the population attributes into that. So addresses and then pop dataset, and for here we will in the how parameter we will use a inner join, and we can see how that looks later. And then for our predicate we would use a within operation, so that which of the addresses are within the pop data. Okay, so we run this, and then we get the error of the predicate. Let's use the old one for now, called up. That seems to run without any warnings. Okay, so we will keep using that. So yes, doing the now we have done the spatial join. We can take a look at how that data frame looks. Looking at the head of it, we see we have the addresses or our initial addresses data frame, and to the right of that we have the index right and the pop 18 column. So what we have gotten here is we have the index right, which matches up with the index of the polygon from the pop data frame and the corresponding population count in the pop 18 column. All right, so that was our first successful spatial join. So let's now take a look at how our data looks. We can check out how many rows there are in our new geodata frame. We have 31 rows of data, and then we can check how many of the addresses, how many of the addresses in our original data frame are still in our joined data frame. So if we check the length of addresses, we see it was 34. So that means that we had 3 addresses that did not match up within any of the polygons in our population data. So they were outside, and as we did a within operation, then they are then lost from in that new Geopandas data frame. So we can try to look at that visually to see if we can spot why that has happened. So let's create a figure and plot the data to that. We will take if we first start with the population grid, and we can plot that to the axis. If we just plot that, we should see these are the grid cells and polygons, and we can plot the addresses on top of that to see if we can spot any points that falls outside of the population data. So we can give those a red color and a marker size since they are points, and just quickly plot that to see. And if you can see that many of the points are located here in the center, but there are also some points like this that seems to be falling outside of the population grid. So that's why those three points were not kept in the spatial join data. And then there was a question in chat about the how parameter, and yes, we can take a look at that. If we scroll a bit up again, we can see we had a inner join here. What we can do if we quickly take a left join instead and see how that looks, we can see that we have 34 rows in our joined data, because we on the left side try to join in all the population cells. So it keeps the entire addresses data frame and then joins in data to the left of that. Whilst as the inner, it takes only the ones that match up, and then those from addresses that didn't match up to the point or the polygons, those are then dropped from the data. And the same goes for the right. So yes, that's how the how parameter works. But we'll go back to the inner and have the 31 rows, and then we have plotted it again to see that. So here, yeah, we plotted with the original points, but we can also take a look at the joint data that we now have and try to plot those points. So if we indeed here create a new figure and start with our join data and plot that to our axis, we can see we get the all the different points plotted. But what we then can do, since we have take in the population data from the population request that we did and merged that into, or made a special join into the data. We then have also the information about both the points, but also the population. So we could then select the column that we want to plot out. So if we take pop 18 here and try to plot that, it might be a bit difficult to see, but we can see that we have some different colors that are plotted. We can try to make it more clear if we choose a color map with the CMap parameter. Take the reds. We can see now. We can more clearly see how the data looks, and we can also we will be getting into classifying data in the later weeks, but we can choose a classifying scheme. Let's do quantiles and then also add a legend. So put legend true. If we plot that, we can see how many of the inhabitants living close to each of the points. So here we can then see what the different points mean, and we got the population data merged into those points of addresses. Okay, I hope that made some sense. We can, yeah, using the same principle for plotting, we can also plot the population grid to check the population distribution, not just for the points, but for the entire grid. So if we, here we have it already printed out. So if we run this cell, we are using the pop data frame, using the population axis or column with the same scheme. So we here see where the population density, or where the population is distributed in Helsinki, and in that sense, this makes the points also aligns with the distribution here. Okay, so we can, in the end, we can save our merged data, spatially joined data, into a shapefile that we can use later on as well. So we can do that by saving to file. Okay, that was a spatial joining.